The map we had of the Milky Way in 2014 was wrong. Not slightly off, not a rounding error. Fundamentally, structurally, embarrassingly wrong. And the wild part, we didn't even know it yet. 10 years ago, our best picture of this galaxy, the one we live inside, was essentially a sketch built on guesswork. We knew we had spiral arms. We knew there was something massive at the center. We knew we were somewhere in the outer third of the disk. But the details, the precise positions of a billion stars, the true mass, the real shape, we had almost none of that. We were navigating by candlelight inside a building we'd never seen from the outside. What happened between 2014 and 2024 was not incremental progress. It was a complete reconstruction. Scientists didn't just update the map, they threw it out and built a new, one from scratch. And the galaxy they found looks nothing like the one in your old textbook. Here's where we started. Before Gaia, before the Event Horizon Telescope, before any of the breakthroughs you're about to hear, astronomers had cataloged the precise positions of roughly 100,000 stars in our galaxy. 100,000? Out of hundreds of billions. That's like trying to understand a city by visiting 3 city blocks. We knew the rough layout. We had reasonable guesses about the number of spiral arms, but the structure beyond our immediate stellar neighborhood was essentially extrapolation and assumption. Then, on December 19, 2013, the European Space Agency launched a satellite called Gaia, and from that moment forward, nothing in galactic astronomy would ever be the same. Gaia's job sounds deceptively simple. Look at stars and write down where they are. But the precision involved is borderline incomprehensible. The satellite measures stellar positions so accurately that it's the equivalent of standing in New York and resolving a coin sitting on the ground in Los Angeles. It does this by measuring something called parallax, the tiny apparent shift in a star's position as Gaia orbits the Sun across 186 million miles of baseline. From those tiny shifts, it derives real distances, and then it watches those stars move, night after night, year after year, building up velocity profiles for over 1 billion objects. The first data release, DR1, came in September 2016. Useful, but a warm-up. DR2, in April 2018, was the one that changed everything. Precise positions, distances, and velocities for 1.3 billion stars. By the time DR3 dropped in June 2022, that number had grown to 1.8 billion. 1.8 billion individual stars, each with a measured location in 3-dimensional space. Think about what that means for the map. Where we previously had 3 blocks, we now had the entire city, and the suburbs and the farmland beyond, charted down to the individual house. Astronomers found that the Milky Way has not 4 spiral arms as once thought, but at least 7, with the local arm, the one we live in, stretching at least 26,000 light-years, far larger than anyone believed. The Perseus arm turned out to sit at a completely different angle than models had predicted for decades. What we thought was a fairly clean, symmetric pinwheel galaxy turned out to be messier, patchier, and far more complex. But Gaia didn't just show us where things are. It showed us what happened to them. And buried inside those billion stellar velocity measurements was a ghost. In 2018, astronomer Amina Helmi and her team at the University of Groningen were sifting through Gaia DR2 data when they noticed something strange. A large population of stars in the inner halo of the Milky Way, stars close to the galactic center, were moving differently from their neighbors. Their orbits were elongated, slightly retrograde, kinematically weird. And when the team traced back where those orbits came from, the answer was staggering. These weren't Milky Way stars. They were the remnants of a completely different galaxy. About 10 billion years ago, a dwarf galaxy, roughly the size of the Large Magellanic Cloud, now called Gaia Enceladus, came crashing through ours. The collision was violent enough that it heated and puffed up the Milky Way's thick disk, fundamentally reshaping the structure of our galaxy before most stars in it had even formed. What we call the Milky Way today was, at least in part, built from that wreck. The stellar streams left behind, streams of stars still loosely following the debris trail of that long-dead galaxy, covered nearly the entire sky. We just hadn't known what we were looking at. It took 1.8 billion GPS coordinates, and a team sharp enough to notice that some of those coordinates told a story from 10 billion years before anyone was alive to record it. That same year, A separate team used Gaia data alongside classical Cepheid variable stars, a specific type of pulsating star that astronomers have used as distance markers for a century, to do something that had never been done: build an accurate three-dimensional map of the Milky Way disk. What they found was that the disk is not flat. It's warped. Dramatically, unmistakably weirdly warped. Like a record left too close to a heat source, the outer disk bends upward in some directions and downward in others, twisting into an S shape that becomes more pronounced the farther you get from the center. The researchers used 1,339 Cepheids scattered across the galaxy to confirm it. The warp is real, and it's caused by the gravitational torque of the massive inner disk dragging the outer regions behind it as the whole thing rotates. We had suspected a warp for decades. We now knew its shape, its scale, and its cause. Around the same time Gaia was rewriting the structural map, physicists were listening to the galaxy in a completely different way and hearing things no human had ever detected before. On September 14, 2015, at 5:51 in the morning Eastern Time, two laser detectors, one in Livingston, Louisiana, the other in Hanford, Washington, both registered a signal lasting less than a second. A faint chirp in space-time itself. LIGO, the Laser Interferometer Gravitational Wave Observatory, had just detected the ripple produced by two black holes, one weighing 36 solar masses, the other 29, spiraling into each other 1.3 billion light-years away and colliding to form a single 62 solar mass black hole. 3 solar masses worth of matter had been converted directly into gravitational energy and radiated outward across the universe. That energy had traveled for 1.3 billion years, arrived at Earth, and moved each of LIGO's 4-kilometer detector arms by less than 1,000th the diameter of a proton. Albert Einstein had predicted gravitational waves in 1916. For 99 years, no one could detect them. Then LIGO did it in a single second. But the detection that truly blew astronomy open came 2 years later. On August 17, 2017, LIGO and its European counterpart, Virgo, picked up a gravitational wave signal, and this time it came with a bonus. 36 years earlier, no. One would have imagined the following: 2 neutron stars orbiting each other and spiraling together over billions of years, finally merging in a cataclysm 130 million light-years away. The gravitational waves hit the detectors. Then, 1.7 seconds later, gamma-ray telescopes detected a burst of high-energy light. Then, hours later, optical telescopes picked up a glowing fireball, all from the same event, all pointing to the same patch of sky. That event, named GW17817, confirmed in one night what astrophysicists had theorized for decades: neutron star mergers are the factories where the universe produces heavy elements. Gold, platinum, uranium. Every piece of gold jewelry ever worn on Earth was forged in a collision like that. 1. We didn't just detect a merger, we watched the periodic table being written. By January 2020, LIGO had logged something else: the merger of a neutron star and a black hole. A 1.9 solar mass neutron star absorbed by an 8.9 solar mass black hole, a type of event that had been theorized but never confirmed. 3 fundamentally different kinds of mergers, each teaching us something new about how mass concentrates in the universe. And through all of this, one question still hovered unanswered over the center of the galaxy. We knew something was there, something massive, invisible. And 26,000 light-years away, we called it Sagittarius A star. We had watched stars near the galactic center orbited for decades, stars moving so fast they completed full loops around an invisible point in just 16 years. The math said whatever was sitting there weighed 4 million times the mass of our sun, but nobody had ever seen it. On May 12, 2022, that changed. The Event Horizon Telescope, not a single telescope but a planet-spanning network of radio dishes linked together to function as one Earth-sized instrument, released the first image of Sagittarius A star. A glowing ring of superheated gas, 51.8 microarcseconds wide, surrounding a dark central shadow, the point of no return around a black hole, 4 million times the mass of our sun. The technical challenge involved was almost absurd. 3 years earlier, in 2019, the same network had imaged M87's central black hole, a monster weighing 6.5 billion solar masses and sitting 55 million light-years away. That was hard. SGR A-star was harder. It's thousands of times smaller and millions of times closer, but closer doesn't make it easier. Because SGR A-star sits behind 26,000 light-years of the galaxy's dusty core, the radio signal had to punch through enormous amounts of scattering material. Worse, because the black hole is so small compared to M87, material whipping around its event horizon moves at a significant fraction of the speed of light, meaning the brightness of the ring can fluctuate in minutes. The team spent 5 years building mathematical models sophisticated enough to freeze a moving target, extracting a coherent image from thousands of hours of data collected across dozens of radio observatories on multiple continents. What they found matched general relativity's predictions almost perfectly: the ring diameter, the shadow structure, the brightness asymmetry caused by Doppler effects in the orbiting gas. Einstein, again, didn't blink. But here's the thing about SCAR A-star that doesn't get enough attention. Finding it exactly where and how theory predicted it should be is not a small thing. It means the models we use to describe extreme gravity, the same models that describe how space-time behaves near the most violent objects in the universe, are correct down to the image resolution of an Earth-sized telescope. That's not just confirmation. That's one of the most precise validations of a physical theory ever achieved. Now, step back. Add all of this up. In a single decade, we learned that the Milky Way has at least 7 spiral arms rather than 4, with our own local arms stretching far further than we knew. We discovered that the galaxy's disk is warped into an S shape across its outer regions. We found the fossil remains of an ancient galaxy, Gaia Enceladus, absorbed into our halo 10 billion years ago, the collision that essentially built the world we live in. We watched neutron stars merge in real time and identified the cosmic event that makes gold. We saw, for the first time, the object that sits at the center of everything we call home, a 4 million solar mass black hole, glowing exactly as Einstein said it should. And through all of it, the mass of the galaxy itself got revised, upward to 1.5 trillion solar masses, then downward to something closer to 200 billion, as each new dataset forced a reckoning with how much dark matter we can actually account for. As for what comes next, the chapter we used to be completely sure about, that's been rewritten too. In 2012, astronomers used Hubble observations to announce a confident prediction: the Milky Way and Andromeda. Our nearest large galactic neighbor, currently about 2.5 million light-years away, were on a direct collision course, set to merge in about 4 to 5 billion years. It was a clean, satisfying story. Then Gaia got involved. Researchers fed Gaia's precise measurements of Andromeda's motion into a new round of simulations, 100,000 of them, accounting for 22 different variables. And the clean story came apart. The probability of a direct collision within 5 billion years dropped to roughly 2%. The current best estimate puts the most likely merger, if it happens at all, somewhere around 7 to 8 billion years from now. And a 550c outcome, whether these two galaxies actually collide or instead graze and drift apart, cannot be ruled out. The Large Magellanic Cloud's orbit complicates the dynamics in ways the 2012 model didn't account for. We went from a certain future to an uncertain one, simply because our measurements got better. That's the theme of this entire decade. Not that the universe changed. It has been doing what it does for 13.8 billion years. What changed was us. What changed was our ability to listen, measure, and see. We built instruments sensitive enough to detect a ripple smaller than a proton. We linked radio telescopes across the planet to photograph a shadow 26,000 light-years away. We cataloged 1 billion stars with enough precision to identify the ghost of a long-dead galaxy by the way its remnants still orbit. The Milky Way didn't become more interesting. We just got good enough to notice how interesting it already was. So here's what I want you to sit with. Gaia still has data to release. The next major catalog, DR4, is coming. The Event Horizon Telescope is already working with upgraded arrays, collecting data for higher resolution images and potentially even movies of accretion around SGR A-star. And LIGO's latest observing run has already logged dozens of new gravitational wave events that haven't been fully analyzed yet. The decade we just covered rewrote the textbook. The next, one might burn the building down. What part of this surprised you most? Drop it in the comments. I'm genuinely curious whether it's the warped disk, the ancient merger, the gold story, or something else entirely. If this hit the way I hope it did, share it with someone who thinks astronomy is boring. Nothing about a 10-year stretch that gave us the shape of space-time near a black hole and the ghost of a galaxy swallowed 10 billion years ago is boring. Make sure you're subscribed because we're going somewhere even deeper next, and you'll want to be here when we do.